My lecture will be about interfaces and how you define junction conditions for interfaces and how you can ensure that these conditions are satisfied at the numerical level. So I'm going to take information from mathematical modeling in GR and ideas from numerical analysis and take into account new structure for the Einstein equations and questions, advances that have been made about the effect of small scales on the propagation of nonlinear waves. So there will be two main parts in the lecture. In the first part, I will be talking about very simple models, but I believe that simple models can teach you us a lot of interesting things. If you have very complex phenomena, it's very useful to begin with simple models. And the setup, what I have in mind are the dynamics of complex fluids. So I guess in this community, we should think of modeling of neutron stars and situations where you may have non-convex equation of states and phase transition phenomena. So you have shocks or interfaces that propagate. And the question I'm asking at this level is, what sort of junction conditions? So you may know from fluid dynamics the usual Rankine-Hugoniot jump relations. And of course, I'm relying on these relations. But my main message is that there are more junction conditions, jump conditions that you have to take into account. So this is important if you want to set up mathematically, make sure that your problem is well posed. And then it's also very important to make sure that your scheme preserves this structure. So I will be talking about structure preserving numerical algorithms and junction maps. Sometimes I call them scattering maps. You will see, especially in the setup of gravitational singularities, this is a terminology that we use. I have more materials, but probably I will not have time to talk about it. But I think there is also some interesting structure on formulating hyperbolic equations for f of r gravity in massive fields and advances when you introduce a foliation based on asymptotically hyperboloidal hypersurfaces to foliate your spacetime. And I think not so much has been done in this direction numerically, but theoretically there have been a lot of recent advances. So the last few pages of the talk, you may later look at them if you are interested in this topic. And probably another topic I will not really cover is this question of localization at infinity in space. So in this situation, you want to construct initial data sets for the Einstein equations. So you need to solve the constraints. But what you want to do is that you want to allow your solution to have very different behaviors in different angular directions. And again, there have been advances, theoretical advances in this direction, and schemes that have been used to prove theorems, which I believe are going to be very useful for general relativity and numerical relativity. So I put a few names of my collaborators below, including Bruno LeFloch, Gabriele Veneziano, Tika Nguyen, Yuma, Florian Beyer, and I may mention some other names as I continue. So let me start with this first topic. So we are now talking about constructing an algorithm, numerical algorithm, to begin with simple models, and some of the ideas have been extended to the models I will show you today, but they mostly remain to be done. So for simple models involving several scales, and that's typically what you have in the Einstein equation when you couple with a fluid that has a complex equation of state. There's a number of parameters. that may account for surface tension or Hall effect in magnetohydrodynamics, for instance. And these parameters are in competition in physically in a model, and even more numerically when you compute your solutions. You have to be very careful about the scales that come from the fluid, the scales that are associated with the geometry. And in the end, you may observe very fine scale structure that you could think in a first, in the first step, you think that these are oscillations, maybe turbulence effects that you could just forget in a first approximation. So I guess this is correct. But since now the machines are improving and the technique of machine learning are telling us that we can go much further in a modeling, you have now to pay attention to these effects from the small scales in the problem. So I put here a number of keywords to tell you what I have in mind of shocks or material interfaces, possibly material undergoing phase transformations. Basically, there's one issue, which is a lack of convexity of the equation of state. And the other issue, and they are related, is a lack of regularity of the geometry. When you approach your interface, the geometry may be regular, but the fluid is discontinuous, say, or the geometry itself may be singular. And I'm interested in both situations. And even more, I'm interested to merge ideas that come from both directions. So in a regime where you have several scales, it's important to understand what are the variables that have a well-defined limits. If you have oscillations, if you have blow-up, you need to extract certain variables that have well-defined limits. So this is part of the mathematical or physical analysis of the problem that you have to do first. What quantities are really meaningful near the singularity, near the interface. And after you have done that, you can go to the next step, which is to analyze how you make a junction between fluid variables or geometric variables on both sides of the interface. And again, this is a name, scattering laws, that I'm using in that, or also kinetic relations is also a terminology that describes these junction laws. And a typical situation which I want to show you first is a situation where you have a shock in a fluid, and this shock, the characteristic phenomena around the shock, makes this shock undercompressive. And I explain next what it means. But the main point is that these undercompressive shocks, or subsonic phase boundaries, in the case of phase boundaries, determine the global dynamics of your solution. So they are essential. I mean, you cannot forget about the effects. They come from small scales, but they have an effect at a large scale. So I'm going to explain this in a simplest model I can think of, which is a Burger's kind equation, where the flux, instead of being rho squared that you know for Burgers, here it's taken to be rho cubed. So it's a non-convex equation, flux, for this conservation law. It is a very simple model describing phase transitions. In magnetohydrodynamics, you have essentially exactly this equation in some limit for the transverse component of the magnetic field. So here I'm producing a model that is very, very simple, but it's very useful to understand the phenomena. And I'm taking into account viscosity effects, surface tension or capillarity with a parameter kappa. And what I do now is that I show you the result of a Riemann problem, meaning two constant states separated by an initial discontinuity. And I want to know how this initial discontinuity will evolve in time. So it evolves in a certain self-similar way from the initial discontinuity locus. And it has the following shape that you see. There are, in this situation, two shocks. And so the point is that if now I let these parameters to be very small, which they are physically, viscosity and capillarity, they are very small coefficients. So this is what I get. In the first picture, it's not they are not very small yet, but if I do it I show it to you in the second picture, you really see that the solution of this Riemann problem, a single dam, it's also called dam breaking problem. Instead of having one wave, which is what you should have, because there is just one conservation law. So normally one conservation law gives you only one wave, one shock. But here you see two shocks. And these two shocks are, well separated. They propagate with different speeds. One of them has slight oscillations. So these oscillations are actually very important, and they determine the global dynamics of your solution. But these oscillations are, they are not there. They do not make the solution unstable or anything like that. There is a definite limit to this process. So let me show you the effect of, let me first say that we have several regimes in this situation. So we have several physical parameters I call epsilon kappa in this problem. There may be more. And there is a natural scaling in this case, which is epsilon square and kappa. So in a given flow, you may have regions where you are in one of the three regimes, meaning that the viscosity is dominant. In this case, you will observe a single wave in this example, or the oscillations are dominant. In this case, you will not observe shocks. You will just observe oscillations and a very noisy pattern, and not something that you could describe with a sharp interface model. And this is my objective here in the discussion, is to tell you that there is behind this problem a sharp interface modeling that is interesting in certain part of the flow, not everywhere, but in certain parts of the flow. And the part of the flow where you have to be careful about the effect of these small scales is in the so-called balance regime I put in red, where the scaling of the small effect due to the capillarity and the small effect due to the viscosity are kept in balance. There is a limit, and numerically it is there. And then comes a lot of questions, based on this model. Does that exist for other models? And the answer is yes. And then can you parameterize, if there are new waves and new wave pattern, you should be able to parameterize them. And there are junction conditions that describe that. They are called kinetic relations in this situation of fluids. So the second part of the talk, we'll be talking about gravitational singularities, and I will be telling you about these junction conditions, how I derive them. But at this level, this is not my point at this moment. My point is just to show you that these things exist. They are stable, and it's important to compute them numerically in an accurate and robust way. So I show you a second example where now I have two conservation laws. And the equation of state, again, is non-convex and is given by van der Waals fluid. But basically, any non-convex pressure density law would give you what I'm describing today. So you see now two plots corresponding to the mass density of the fluid and the velocity component. You have now a wave pattern that is more complicated because you have two equations, so you should expect two waves. But in fact, if you look carefully, you have actually more waves. In this situation, the wave pattern going to the left contains a rarefaction, then there is a constant state and a shock, which is actually more like a phase transition. It depends on the values of the parameters. So it's really the analog, what I show you with one equation, that also occurs with two equations. Each wave has the same double wave pattern, possibly double wave. In this case, one has a double wave and the other wave has two single wave. I mean, left and the right, maybe I'm not explaining very clearly. But okay, now the main point is the following. If I change the parameters epsilon and kappa, I already show you that the solution there is some effect of these small scale parameters. But now what is very interesting is that if I change the ratio between kappa and epsilon square in this situation, I find the picture that you see, the one on the right, which I show you again in this page. And so you see now that the solution at the macroscopic level, everything is obtained under convergence of your scheme and with parameters that are very small, but the ratio between the two physically significant parameters is different. Only this ratio is different, but both parameters are very, very small and can be arbitrarily small. And this is what you observe. You just observe different solutions. Okay, so you vary this ratio, you get different solutions. So the physics is there. Or any of these solutions is as physical as the other and another one. And you need a rule now for understanding how you connect left and right state values at these interfaces. So you need to go beyond the standard Rankine-Hugoniot relations, because all these waves I'm showing you are in agreement with the usual jump conditions that you know for hydrodynamics in textbooks. So there is something more that you need, which is this junction, scattering maps, kinetic function for the interfaces. So I don't have time here to continue in this direction, but this is one typical situation where you need some extra information, and then you need to construct your scheme in a way that preserves these structures, these hidden structures that you have found. You can do that by a front tracking scheme where you follow the interface and somehow you exactly impose your correct jump relations that you have derived by some asymptotics process. Or you may use shock capturing, but if you do that, you have to be very careful about the dissipation, and you need it to be well controlled in some sense. So I'm not continuing in this direction here, because this is really just an overview. So I'm showing you now a second situation, maybe closer to the interest of this community, which is a formulation. Again, it's a model. So I fix the geometry to be an FLRW type cosmological background with certain small inhomogeneities that I just put by hand in a metric. And now in this background, I look at a fluid which is 2 + 1 dimensional, isothermal, relativistic, and I look at both directions, future contracting or future expanding. But maybe in these slides, I'm just showing the direction going towards contraction, the singularity, because it's very much connected to what I will present you next. So here we are interested to evolve this, let this fluid evolve toward the singularity. The equations are put in a nonlinear hyperbolic form as usual, and you have now two competitive effects. You have the geometry, which is contracting, and you have also the propagation, the shock propagation that has its own speed of propagation. There's some interaction taking place, nonlinear interactions. And so again, you expect, or at least I expect, to see some small scale structure, which in this case is going to be driven by the background geometry. So maybe it's not so exciting, but still it's interesting to see, and I see an analogy with what I just show you in phase transition. So how do you attack this problem if you want really to be precise about capturing the correct asymptotic on the singularity? So the structure preserving methodology that we use is, first of all, to use a divergence form of the Euler equations, like you should, by using a finite volume scheme, which is shock capturing, and will ensures that the speed of propagation of your shocks are going to be correct. In a high accurate scheme, fourth order in time, second order in space, make sure that you don't introduce additional oscillation from the scheme itself, the discretization. And then we have, then we have the main part of the work is, first of all, to write with certain rescale unknowns. The solution, the density, for instance, will blow up on the singularity. So you have to rescale that. And the way you do it, again, this will become more clear with the second part of the lecture. The way you do that is by doing a Fuchsian analysis. So you know that your PDE has certain 1/t contributions. So you need to expand your solution with some certain ansatz, and even if you don't prove or try to prove a full theorem, you need to have a quite good ansatz for the asymptotic of the density, the fluid. At this level, the geometry again is fixed, but the geometry will come next. So you need to input that. Then, so these equations, certain asymptotic state equations should be input at the discrete level. So the idea is that the asymptotic analysis will tell you that certain terms are negligible when you approach the singularity, and you have to make sure that your scheme is consistent with this intuition and these ansatz that you are able to build. And the way I somehow quantify this work and for the Euler equations, I mean, there's a lot of constructions that I cannot show you here, unfortunately, but the main point is that you want to enforce this commutation property. So when you approach singularity, so t going to 0, you want some certain commutation properties that takes place when you approach the singularity, or when you refine the discretization parameter. You would like this two limit to commute. So maybe I will not say more here and show you the results of the typical behaviors that we find on the singularity. So this is a picture of rescale quantities for a plot of the rescale certain velocity component and the rescale density. And this is what we see. So we see a certain pattern and structure of the singularity. So which is by itself, essentially it comes from the geometry that has driven the solution to be that. But what is interesting is that even though we compute singular quantities, we have a very good convergence process. So you see various steps of convergence of t that goes from 10 to -5 to 10 to -12, and we check very carefully the convergence. And if you don't do all the rescaling I talked about before, and a specific construction that allows you to commute these two limits, you would not get this good agreement. And I'm going somehow to show you, to try to illustrate that with a picture in 2D. So this is a picture for the velocity magnitude of, I compute in a box with certain periodicity condition. And the two pictures that I can show you is a case where I do some standard algorithm where I will not enforce this commutation condition, and I get this picture. And if I enforce it, you can see somehow some rather interesting effect that the fine structure is really significantly better. Now, I have a third example where a structure on the singularity needs to be computed. So let's now look at a fluid again on a Kastner geometry. So it's now going to be spatially homogeneous, anisotropic. So it's a vacuum solution of Einstein with certain Kastner exponent, parameterized with a parameter kappa. And I evolve on this geometry a fluid, again, the same equation of state. And by a certain theoretical studies that we did, Florian, Bayer, and myself, We found that by an asymptotic analysis of the fluid behavior near the singularity, we found that there is a parameter, we call it capital gamma, defining a certain subcritical or supercritical behavior for the fluid. And when this parameter gamma is positive or between 0 and 1, the fluid turns out to be dynamically stable on this Kastner geometry, but it is unstable in the supercritical regime where this parameter becomes negative. So we have some theoretical study of that, and we found that our theorem could not apply in the unstable case. So hopefully our next work will be to study the unstable situation, but today I'm only telling you the stable situation. And in the stable situation, we developed a scheme. Maybe before that, let me emphasize that the way we figure out this parameter gamma, big gamma, is by plugging a certain expansion in power of t. That's what you expect, to have a certain power of t of behavior, and we attempt to validate it. And by trying to validate and to make sure that the right-hand side, the source terms are small, we found this condition on this exponent. So now the scheme is obtained by writing the hyperbolic formulation of the problem. It's a singular initial value problem. And now the way we attack this problem is to put data on the singularity itself. Okay, so you have two ways to attack this sort of problem, to start from the singularity or to go toward the singularity. But in this part, we were interested in starting with data on the singularity and trying to parameterize the solutions. So we are in the shock-free regime. We defined a pseudo-spectral method of lines for the Euler equations on this Kastner background. We use a high-order Runge-Kutta discretization. And again, we introduce suitably rescaled variables that come from our analysis. So really, my message is that you cannot skip the part where you do the analysis, a very careful analysis of your PDE, in order to be able to define the scheme and make sure that you preserve the structure of the equation. You need to know the structure in the first place. So we do introduce suitably rescaled variables again. And what we have done here is to carefully study the source of numerical error in this situation. So we have a singular PDE. It has 1 over t terms. T goes to 0. It's really singular. And what we have understood here is that we have actually two sources of error. One that comes at the continuum level of modeling, in the sense that we cannot solve the equation exactly on the singularity. So we need to do some kind of extrapolation and solve at a small distance from the singularity. So this introduces an error. And we have also a discretization error from the algorithm itself, the main part of the algorithm. So what we figure out by doing a study of this flow on Kastner is that what was best was to keep these two errors asymptotically in balance. So this is what we have proposed in this work. And with this numerical strategy, we were able to demonstrate the nonlinear stability of the flow near a cosmological singularity in the subcritical regime. So in fact, we had a proof of that, but for us, this was a way to somehow further validate the analysis. So I'm just showing you this picture here, and it's probably good now if I move to the second main topic that I want to show you. So here you see, let me just repeat that we have a reliable, accurate algorithm. We check very carefully the numerical error. And despite the solution being highly singular, we were able to compute the solutions with a high degree of accuracy. So we are working on taking the self-gravitation effects into account, but this is not yet finished. One of the reasons is that traveling and has become more difficult, and my collaborator, maybe you saw it, he's in Dunedin in New Zealand, very nice place, but it's a long trip from Europe. So let me now, except if you have questions, maybe I don't know if I should stop and ask if there are any questions.
Any questions in the room? Anyone online? Doesn't look like it, so please continue.
Okay, so let me move to the second topic, but it's really very much related to what I just told you, except that now I'm going to focus on singularity, gravitational singularity, and I'm going to tell you. So I've used this as an interface, as you will understand, and I'm asking what sort of junction should be put at this interface. So the setup, this is a joint work with Bruno, LeFloch, and Gabriele Veneziano. We have a couple of papers that you can find on the archive on this topic. And the presentation I'm giving today is a case of a scalar field, a self-gravitating scalar field. We look at bouncing cosmologies. There is a contraction. You reach a singularity. And then I want to define an expansion and connect the two regions of the spacetime. And the part I'm focusing on is the vicinity of the singularity hypersurface. This is unavoidable if you have strong fields. You know that the Penrose-Hawking singularity theorems or incompleteness theorem and the PKL theory will tell you that singularities are there. So you need to say something about them. And as far as the junctions are concerned, Penrose is probably the first person to have looked at that, and a number of other people after him. But essentially all the proposals that exist in the literature, and I will put more names in a minute, they consider symmetric spacetimes, and they consider spatial junctions, and they tell you that this is how you should do the junction. So this is not going to be our point of view, and really motivated by what I presented for phase transition and these kinetic relations that I know and have worked on for 10 or 15 years. This is not the point of view I want to take. So I would like to formulate the problem by having in mind that there are classes of physically meaningful junction conditions that I would like to exhibit. And I ask the question, what are the degrees of freedom? What are the constraints at the singularity across the interface? And we, to tackle that, we introduce what we call singularity data, which are exactly in the spirit of the previous discussion. You do some asymptotic analysis and you extract some quantities that have a definite limit. And these are the data that you can talk about on the singularity. I call them GK5051 for the metric extrinsic curvature and matter fields. And what we call a singularity scattering map is a map that takes data before the singularity and give you the data after the singularity. And the question I'm asking here is, can we fully classify all the possible bouncing laws at this singularity? And the answer is yes. And interestingly, we should distinguish between universal laws and model-dependent laws. Exactly like what I briefly discussed before for fluids and phase transitions, where you have Rankine-Hugoniot relations on one hand, and they are not enough, and you add these kinetic relations to describe fully the dynamics of the interface. So we do exactly the same here, I mean, philosophically at least. So here I put a number of names and models that some of you, maybe most of you, will know. Pre-Big Bang scenario, modified gravity matter models, loop quantum cosmology. So in a second stage, we will look more carefully at these different models, but for now we have not done that because again, our standpoint, so I'm trying to summarize the main message, is that scattering maps, of course, should be associated with some certain specific series, but we have the possibility to produce a flexible framework and to produce a classification that tell you all possible junctions that are physically and geometrically meaningful. We have subclasses in our classification that we call conformal and non-conformal. We cover space-like, null or time-like hypersurfaces. Maybe time-like hypersurfaces would be closer to what I discussed for fluids before. But I guess most of my presentation is more focused on the case of a space-like hypersurface in a situation of contraction and expansion. We cover various models and we have a complete classification of that. And as you will see in a few minutes, we have three universal laws that constrain the macroscopic aspects of space-time bounces, regardless of their origin from different microscopic corrections. So we have a guide to uncover the structures, and we need to go back to the physics, I mean, some additional physics to produce a structure. And we need also to use the techniques of structure preserving, these structure preserving algorithms in order to make sure that these junctions are satisfied numerically, right? So there are a number of directions that we have not covered, investigated yet. So I'm really focusing on one question today is how you actually formulate the problem. And I believe that we have the right formulation and we can really carry all the physics that is relevant here. So I'm going now to show you more details about our junction conditions for gravitational singularities. And I'm going to do that by starting with ADM formulations that I guess everybody will know. We also write the constraints. And in fact, the constraint will be more important to us than the evolution equations. So the point, when you want to analyze the behavior of your metric and fluid variables near singularity, you do what I mentioned before. You do a BKL, you use BKL and that, or also called a Fuchsian approach, where you expect that phenomena will be basically determined by ODEs in a time variable. So you replace, but it's not quite true. But essentially you replace the Einstein equation asymptotically by a system of ODEs that give you a first ansatz, a first term in your ansatz if you want to produce some asymptotic behavior. It's also called velocity-dominated ansatz. So you may want to put data on the singularity and solve toward the past or toward the future. So this is done by this ansatz, and to be more precise, to do that, I produce a profile for the extrinsic curvature, which will be 1 over tau. Tau is my time, Gaussian time variable, times a constant. I mean, it's not constant. It depends. Of course, it's a tensor on the singularity hypersurface. This is for the extrinsic curvature. The matter field behave like a log of tau, and the metric, yeah, right. On the top here, you see the expression of the metric, which is more complicated because it contains an exponential matrix. But in any case, if you give me some data, G minus K minus phi 0 minus phi 1 minus. These are fields defined on the singularity hypersurface. Then I can produce an ansatz, a first term in an expansion of the solution of the Einstein equations. So this is what I do, profile based on singularity initial data set. But now this initial data set cannot be arbitrary. It has to satisfy the constraints. But what constraints? How do you express the constraints? You express them in an asymptotic way. So this comes from BKL, basically. And the asymptotic constraints tells you that this Riemann metric is arbitrary. K minus should have a trace 1. This comes from the CMC condition of your foliation. The Hamiltonian constraint become algebraic asymptotically, and the momentum constraint is a divergence equation involving also the matter field. So I'm looking at this data. I have a certain space of singularity data, and what I want to tell you now is how I do the junction from a set of singularity data on one side of the interface, I think of it as an interface, to the other side. Okay, so we have a fluid-like interface. The geometry and the matter encounter a jump, but it's even worse than a jump because it's singular. But if you properly rescale, you can really think of it as a jump in the rescaled variables. So I already explained that the effect of certain scales across the interface are essential. So I want now not to introduce these scales at this stage of the description, but I want to remember that these effects are there. And it is these effects that are going to produce a certain Rankine-Hugoniot relation that are universal and a kinetic relation which is model dependent. And another situation maybe I didn't mention is a Martensite-Austenite situation. When you have in material science, this is an interesting application of this concept for two-phase flows. So anyway, in the context of gravitational singularity, let me introduce a notation, capital S, for a map that does what I told you. So I have data on one side to data on the other side. I call this map S, and I require this map to be diffeomorphism covariant, so it doesn't depend on coordinates or anything like that. And also it has to be ultra-local, which is probably from a physical perspective quite natural. Or at least that's what we believe. And by looking at examples, specific models, it seems to be a reasonable assumption. So my assumption is telling me that the junction are pointwise, like what you would do if you write the usual Rankine-Hugoniot relations. Again, you write that and you connect the density and the fluid component on one side to the other side of the interface. And this is purely pointwise. It doesn't involve, higher order derivatives. I guess it could, and there could be jump conditions that are more complex than that. But it's already quite a broad class of junctions that you obtain in this way. So this is essentially our result, our classification. We look at all of these maps, ultra-local, and we classify them. In the course of the analysis, we are led to introduce a couple of conditions to define subclasses of junctions. So time preserving will comes naturally because we actually want to study the case of oscillation-free behavior. So it's also called quiescent singularities. So K is going to be positive. There are two regimes identified by BKL, and we look at the so-called monotone regime that have attracted a lot of mathematical analysis. And so this is a regime that we have studied, and it's also very consistent with what I told you before. So I told you before that I had three different regimes where there could be a lot of oscillations, or maybe the viscosity was dominant, or the viscosity and the capillarity were imbalanced. So somehow we are in a third case that I just listed, and so our map will also preserve this property. So it's so-called time preserving on one side, and it's time preserving, oscillation free, if you want. Now, we do describe a bounce in this situation in the sense that the volume element decreases to 0 when you approach the singularity, and then increases back to finite values. And it does that with a certain geometry and, of course, a certain complex geometry. So we have further notions to describe better the geometry which is behind. And we also consider not only one singularity, but possibly successive singularity hypersurfaces. And we have a notion of cyclic spacetime that we have defined and studied, especially when you have two killing fields. You can define a global construction of spacetimes that undergo contraction and expansion successively. But that's not the purpose of this lecture. In this lecture, I focus on the junction at the bouncing. So here comes the main conclusion for our classification. And the way I show it to you is that I will only show it to you in a restrictive way, which we call rigidly conformal singularity, which I defined maybe in a previous slide. It's a conformal properties that you impose on your data before and after the singularity. So the metric are conformally related. It's not necessary for the classification, but it's just easier to grasp the result, and it was easier for us to do the derivation, to start first with this result. So this is the main point. The main point, you could first think that there are many ways to cross the singularity hypersurface, and just there is no classification whatsoever, right? But there is a classification. And we prove that we have only two classes of ultra-local space-like, rigidly conformal singularity scattering maps for self-gravitating scalar fields. If you do other matter fields, you have to slightly modify the description here. So the first class, we call it isotropic rigidly conformal bonds. And the metric after the singularity is a conformal factor times the metric before. The conformal factor depends on the matter variables before and the determinant of the expansive curvature. K plus after the bounds is just becomes just delta over 3, it becomes basically round or trivial. Phi 0, the matter field also becomes trivial. Okay, so basically you have a trivial extensive curvature. The metric is conformally rescaled, and all the information from the matter is erased. This is one possibility. The second possibility is a non-isotropic, rigidly conformal bonds, where, again, the metric is a conformal multiple of the metric before. But now there is an effect of the trace-free part of K, which is also multiplied by a certain factor, we call it mu, and also there is a certain change of the matter. Okay, so we have the rules, and the rules is explicit in the sense that it only involves a constant C plus, which is mostly irrelevant, and a function. So there is only one function of a real variable to describe all possibilities of bouncing. You can put all the physics you want to supplement, to augment the Einstein equations. You will, across the singularity, taking the limit and only extracting the interesting information at the level of sharp interface description, you will only extract a scalar function of one real variable. So small f will generate a big F and a mu, and you put that in the previous formula, and you have exactly the junction relations. There is a similar, how much time do I have, please?
We actually have 1 minute left. I think you didn't hear me with my 5-minute warning. So let's give you 3 more minutes. Is that okay?
Oh, okay, so thank you, it should be good. So we have a classification which is completely parallel to the one I explained, but removing this restriction of rigidly conformal. It's just slightly more complicated to describe, and slightly more rich in terms of parameters, if you like. But again, there is a finite degrees of freedom. Now, all these results can be restated in terms of three laws, which we called a first law, scaling of Kastner exponents, a second law, canonical transformation of matter, and a third one, which is directional metric scaling. And again, you can see that we have explicit formula. It's really a rewriting of what I explained, at least fully in one special case. And this is a full classification. And you see that very few degrees of freedom appear. So gamma is a scalar constant. And then there is a certain nonlinear map that lives in the space of the matter variable, and certain exponents to tell you how you rescale your metric. Okay, so basically what we have in mind now is to rely on this classification and do a number of numerical experiments, and we somewhat started to do that, but would be very happy to be joined in this project by some other people. If anybody is interested, please contact us. And as I mentioned in the beginning, I'm just skipping the next topics that I wanted to cover, but that will not be for today, but it will be in a PDF file. So please look at that if you are interested. So let me just say in a 2 or 3 sentences that dynamics near Minkowski spacetime in F of R gravity has been done. There is a mathematical solid theorem and techniques that I think are useful for numerical relativity, especially weighted norms that tells you how you can measure the error in your numerical results. So certain weighted norms that take certain asymptotic symmetries into account, and also the foliation based on hyperboloids, which describe a certain region of the spacetime, but some other, time-like direction is described by hyperboloids, and space-like directions are described by asymptotic flat hypersurfaces. And again, we have a lot of mathematical construction that should be used numerically, I'm sure. So let me close with this page to tell you that if you want to read more about the structure preserving method, I put here a couple of papers, review, and the basically two results with Bayer and my former students that I mentioned. Then this work with Bruno LeFloch and Veneziano are mentioned. In particular, if you just want to learn about this topic, you may want to just read this Physics Review D paper. It's only a few pages, and it gives you a summary of what we have done in this direction. And foliation or this asymptotic localization can be found in the last 2 papers. Thank you very much. It was a pleasure to talk in this workshop.